Welcome back, Math 1910, Calc 1. We are in Chapter 4, going through Section 5. We're going to do integration by substitution. We did learn how to do some differentiation by substitution as well. So the fact is, we're going to do U substitution and things like that. So it's going to be very, very similar to that sort of thing, undoing it, but we're going to choose based on pattern recognition. Okay, so we're going to do a change of variables for indefinite integrals, and then when we step into definite integrals, we've got to make sure that we change our limits based on our new variables as well. And then we can decide, on definite integrals, if we have an even or odd function, how it can simplify down a little bit more. But something you really have to hone us in on here is understanding pattern techniques. Essentially, it's to undo the chain rule. So that's the pattern you're looking for is, if I take the derivative of the chain rule, all right, am I gonna, eliminate the stuff where I have to take the derivative of the inside? And I know I keep saying derivative, but we're undoing the chain rule, essentially using U substitution when we go through this. Okay, so if we have, the derivative of the chain rule, right, is the derivative of the outside times the derivative of the inside. So when we want to do the antiderivative, it's the same kind of concept, but we want to use, some sort of pattern recognition to understand that, all right, if we took the derivative of the stuff, would it equal what's next to the integrand based on the chain rule? Okay, and this is a little bit easier to understand as we go through a couple examples in here. And in class, I'm going to go through a lot more in depth on the examples as well. We'll have plenty of examples where we can see how to actually do the U substitution. Okay, but I'll write down theorem 413. Okay, anti-differentiation of a composite function. Okay, that's really what we're going to do. We're replacing the g of x function itself with u, and we're going to replace with the g prime of x dx with du. And like I said, we did this when we did differentiation. We did some U substitution as well. But we're going to change that integral so that we're taking the antiderivative of u du instead of f of g of x, g prime of x dx. Okay, it allows us to take a more complex function, replace it in terms of a variable that's easy for us to do an antiderivative of, and then replace that back later on. So that's the whole point of U substitution, is to create a simpler integral that we understand how to integrate, and then replace, the functions or the variables back. So pattern recognition is very key in understanding how we're undoing, right? Essentially, a composite function is the chain rule. How are we undoing the chain rule? So that's kind of really important here. So let's go through an example where we go through pattern recognition. All right, so if we want to integrate x squared plus 1 quantity squared times 2x dx. Well, we know that we took the integral of something. I'm sorry, not the integral. We took the derivative of something, and it gave us x squared plus 1 squared times 2x dx. We can obviously see with the pattern recognition that 2x, okay, that's the derivative of that inside function, right? The x squared plus 1. The derivative of x squared plus 1 is the 2x. So we know we're undoing the chain rule there. So there's kind of our pattern recognition. So I know that I have to kind of undo the power rule of a square. All right, so now I know I'm going to have an n plus 1 over n plus 1. All right, n being 2, that's the exponents. We've done this before multiple times with some other integration. So I know that when I simplify this down, okay, I want to be able to say, all right, I'm going to have x squared plus 1 to the third divided by 3. Because I know if I take the derivative of that, the 3 will cancel. I'll be left with the x squared plus 1 squared, and I'll have to take the derivative of the inside stuff. The derivative of x squared plus 1 is 2x. So we're going to be undoing the chain rule when we go through that. So it's being able to recognize the pattern there, okay, and then undoing the power rule. So like I said, if we can see that we have f of g of x, it's a composite function, right, because it's x squared plus 1 quantity squared. It's a power rule for us. And we can see that we have g prime of x, that's the 2x. So hopefully you're starting to recognize the pattern here. So I undo the power rule with the x squared plus 1 quantity squared. Right, so like I said, that's n plus 1, so 2 plus 1, so it's to the third, over n plus 1 divided by 3, right? So that's why we have the 1/3 x squared plus 1 cubed plus c. Don't forget the constant of integration because this is an indefinite integral. So don't forget about that because we need to go back to that. We spent the whole last section doing definite integrals, so there wasn't a plus c because we were doing all that evaluation. But remember, anytime we have the indefinite integral, we have to do the plus c. So there's using pattern recognition. And if you can't see the pattern, our fail-safe is going to be like our next example where we learn to use substitution. It's a little bit, more involved, but it makes sense. So if you're struggling to see the pattern here, that's okay. Substitution makes it even easier to kind of see and to apply. Okay, but remember, with all of these, if you take the derivative of your answer, you should get what's next to the integrand. If you don't, all right, you took your antiderivative incorrectly and need to fix that. Okay, so pattern recognition, very important. Sometimes, you have a constant function in front, so you can pull that constant out and still do the integrand, just like we've done before. It's just a multiplier. All right, and if you want to see more of that, all right, we'll do an example here. Now, we have to check out what's going on here. We have the integrand of x times x squared plus 1 quantity squared dx. Now, look, if we undo the chain rule, right, the derivative of the x squared plus 1 is 2x. Well, something happened, right, that we're just left with an x now, and we aren't left with a x over 2. Something canceled, all right? So we got to think about the pattern there that's going on. It's still, a chain rule undoing. We still have to have an x squared plus 1 to the n plus 1 divided by n plus 1. So we know that we're still going to have x squared plus 1 quantity cubed divided by 3. But we have to do something else here, because the derivative of that chain rule piece, that inside piece, x squared plus 1 is 2x, and we're only left with an x here. So something happened that undid a 2 in front. Okay, so you need to recognize that. But it's very, very similar to the first example. All right, example 1 was identical to this, only it was 2x instead of x. So you just got to make sure that you pay attention and look for, what's missing. Okay, so in this case, that 2 that was in front is missing. So we have to know that we have to be able to offset that. So what we can do is know that, all right, that 2 disappeared. How do we make a 2 disappear? We multiply by 1/2. Okay, so now we can say that there was a 1/2 in front of that integral, because multiplying by, and dividing by 2 at the same time. So multiply by 2, divide by 2 is essentially 1, right? And we can multiply anything by 1 and we don't change it. So that's really kind of the rule that's in effect here. The original function of that, if we rewrite it correctly, okay, and we have to rewrite that original integral at the top, right? The original integral at the top is x times the quantity of x squared plus 1 quantity squared dx. And we recognize the pattern was very similar to the first example, okay, only the 2 was gone. So we had to do something to counteract the 2. So we can multiply by 2 over 2. All right, that's the form of 1. And then we can rewrite the integral. So I can say that it's 1/2 times the integral of x squared plus 1 quantity squared times 2x dx. Now that's exactly like example 1, only there's a 1/2 in front. Okay, and that's completely valid. We multiplied by 1 in the form of 2 over 2. Why? So that we know that we can do the antiderivative of the, we know how to do the antiderivative, right, of x squared plus 1 quantity squared times 2x. Okay, so we had to be able to cancel that x in front. So hopefully we're seeing why we had to do that 1/2, because you're going to have a lot of problems like this where we've got to see, that value has to be canceled out. So now when we do the antiderivative, it's just like example 1, only now that there's a 1/2 in front, you're going to have 1/2 times that 1/3, so we're going to have 1/6 in front. Okay, so when we integrate, okay, constant of integration, don't forget that. We've already done this integral in the previous example. All right, now it's just 1/2 times it because that 2 canceled. All right, so we can literally simplify this down and write it as 1/6 times the quantity of x squared plus 1 cubed plus c. Okay, so don't fret, but lean back. And like I said, if you have issues, the next stuff that we're going to go through is going to help that. If you can't see the pattern and do the pattern recognition, that's fine. Okay, we have ways around that. And it's called change of variables. This is where we are going to do U substitution. So we're going to recognize that we got a chain rule or a composite function that we have to do the antiderivative of. And sometimes it just doesn't work out well. So we're going to use things in terms of U and du. The U and du make it a much more convenient integral to integrate, so that we can undo things, and then we replace what U and du stands for, once we've done the integration. So it makes it a little bit simpler for us as we go through this. Okay, so we can rewrite the composite function in the form of a U function, okay, so that it makes it easier for us to do. So how do we do that? All right, so when you're choosing U, generally choose the more complex piece. Okay, so we have the integral here of the square root of 2x minus 1. Okay, now normally, right, we're going to take 2x minus 1, we're going to rewrite that as x to the 1/2. Not necessarily, we could do it the other way, recognizing patterns and undoing the patterns and things like that. Or we can make this a much simpler integral, and we don't have to worry about, like example 3, do I need to multiply by a half in front or things like this. This really helps it work out when we do a change of variables. So, generally when we have a square root of function, you're going to want to choose whatever that stuff is under the square root to be your u. So we're going to let u be 2x minus 1 here. Okay? Then when you select your u, you need to take the derivative of u with respect to x. Alright? So you're going to know that du is going to be 2 dx. And we have to replace some things. We have to replace dx as well. So since we know, alright, the du is going to be 2 dx, right? I'm just taking the derivative of the u function with respect to x. I know that dx is equal to du over 2, okay? So when I do that, I can substitute back in. So I rewrite the integral now all in terms of u. So I replace the 2x minus 1 with a u. So now I have the integral of the square root of u. The square root doesn't go away. Okay, when you choose u, don't choose the square root of 2x minus 1. Just choose the quantity that's underneath the square root sign. Alright, so we're going to get the integral of the square root of u. Then we have to replace dx. dx is du over 2. So this helps us with that 1/2 issue that we had like in example 3. So remember that you will always have to solve that du derivative piece for the dx. Sometimes you will have to divide by a constant and move it over and replace. Sometimes you won't. Okay, sometimes it'll work out perfect. So now we can do the integral in terms of u. You can rewrite that square root as u to the 1/2. Okay, and now we have a much simpler integral to work with, right? It's easier for us to take the integral of the square root of u instead of the integral of 2x minus 1 and recognize the patterns in undoing those things. Okay, so now if we want to do that, please remember always rewrite the square root function as a 1/2 and pull that constant in front. So since it's du over 2, right, we can rewrite that as 1/2 times the integral of u to the 1/2 du using our constant multiplier rule. Okay, when we integrate this, okay, now we get u to the 3/2 divided by 3/2, right? Because we're undoing the power rule, so it'll be u to the n plus 1 divided by n plus 1, and n is 1/2, okay? So we're doing the antiderivative. Don't forget the plus c, okay? Then you're going to multiply by 2/3, all right, the reciprocal of the denominator, and the 2's are actually going to cancel out. So when we do that, we end up with 1/3 u to the 3/2 plus c. Now we're not done, right? We did all this integration in terms of u. Okay, this is where we have to bring back what u is. All right, so we're going to replace u with its x terms, okay? Because our original function was doing this in terms of x. So now I replace u with what we used before. Remember earlier we said let's let u be what was under the radical, which was 2x minus 1. Now we replace u with what it's equal to, 2x minus 1. And this would be our antiderivative, and this would be our indefinite integral solution, 1/3 times the quantity of 2x minus 1 to the 3 halves plus c. So when you do these problems, all right, you got to select u, take the derivative of u, and then replace u and into the function, into the integrand, and you're going to rewrite du into the integrand. You're going to integrate in terms of u. Once you're done with that integration, you're going to replace what u was, all right, back into the final answer. So fairly easy. All right, we're going to get a lot of practice on this in homework, or during homework. Okay, so here are some basic guidelines for making changes of variables. Make sure that you guys write these down, and as you're doing your homework assignment, I would have these guidelines, next to you. So first one, right, choose a substitution, u equals g of x. It's always best to choose the inner part of the composite function. So anything that's raised to a power, right? So if I had like, x squared plus 1 quantity squared, right, I would choose the x squared plus 1 to be my u. Just like in example 4, right, we had the square root of 2x plus 1. Well, we chose u to be the 2x plus 1. So choose what's under the square root. Okay, choose that entire kind of piece, and you'll get used to this as you do more and more problems and things like that. Then we have to find what du is. Du is, we have to take the derivative of, once we choose u, all right, we're going to take the derivative with respect to x. Okay, then we're going to rewrite the integral in terms of u and du. We're going to integrate in terms of u, and then we're going to replace u back with what it was in terms of x. All right, and then you can always check your answer by taking the derivative of it. Okay, and this is the general power rule of integration. I gave this to you before, okay, so that it makes it a little easier. All right, but when we do this, all right, it's g of x to the n plus 1 divided by n plus 1 plus c. As long as n is never equal to -1, this works out. So generally, why do we use that? Because when we use u substitution, as you see below, right, the integral of u to the n du, that's a much easier integral for us, right? It's just u to the n plus 1 divided by n plus 1, plus c, because it's an indefinite integral. So it's much easier for us to take that composite function, and use it in terms of u instead. Okay, so let's take a look at some examples here of when we want to choose those, what's good for choosing u. We can see that if we let u be 3x minus 1, all right, we can know that du, so the derivative of 3x minus 1 is just 3, which is what we have in our integrand. It's 3 dx, right? So we know that we can replace the 3 dx with du, and then I know that if I take, the derivative of, I rewrite 3x minus 1 with u, it becomes u to the 4th. So I know that I can take the integral of u to the 4th du very easy. All right, u to the 4th integrated is u to the 5th over 5. Okay, so once I know that I have u to the 5th over 5, I replace u with what we said it was before. It's 3x minus 1. So we do that replacement. Don't forget the plus c. All right, let's do another example here. If we have two functions multiplied by each other, this is a little bit pattern recognition, all right, but let u be the more complicated one. U needs to be the more complicated one. The more complicated one is the x squared plus x. All right, so x squared plus x will be our u, and then if we take the derivative of x squared plus x, we get 2x plus 1, which is the other piece of our integrand, right? That's our du. Our du is 2x plus 1 dx. So now we can replace that entire 2x plus 1 dx with du. And we literally just have u to the 1st. And now we know how to take the integral of u du, all right? It just becomes u squared over 2, all right? So we get u squared over 2, and then we replace u back with x squared plus x. So our final answer here would be x squared plus x quantity squared over 2 plus c. So hopefully we're getting the gist of u substitution here. Now if we look at the next one, remember, let u be the most complicated piece. The most complicated piece is what's under the radical sign. Okay, what's under that square root sign. So x cubed minus 2 will be our u. Then we have to take the derivative of x cubed minus 2 to get our du, which gives us 3x squared dx. So now we can replace the 3x squared dx with du, and we rewrite the function in terms of u. So we're going to have the integral of u to the 1/2 du. Okay, and n is our 1/2, so we're going to have to do n plus 1, so it's going to be 1/2 plus 1 divided by 1/2 plus 1. All right, and when all that works out and is said and done, we've done our integral, and then we've replaced our, the u back with what it is, x cubed minus 2 divided by 3/2. Okay, and then we have to multiply the numerator and denominator by 2/3, so we don't have a fraction divided by fraction sort of scenario. So we end up getting 2/3 x cubed minus 2 to the 3/2 plus c. Don't forget that plus c with the indefinite integrals. All right, let's look at this one. Okay, well, we have something downstairs now, right? We have something in the denominator when we're doing this. Still let u be the most complicated piece. You want to choose the u to be 1 minus 2x squared. Okay, then you have to do your du. Your du, will be negative 4x dx. And look, that's what's on top. That's a nice replacement. Okay, if you're not getting a nice replacement for most of these, you're doing something wrong or you're choosing u incorrectly. So now let's rewrite u. It's really what? Going to be du over u squared, but we want to bring that u up top so we can integrate it. So it becomes u to the minus 2 du. So when we integrate u to the minus 2 du, all right, we end up getting u to the minus 1 over negative 1 plus c, and then we replace, right, u with what we chose it to be, with 1 minus 2x squared, to the negative 1, all divided by negative 1, all right, and so that will simplify down nicely to negative 1 times, or just negative 1 over 1 minus 2x squared plus c. Last example here, if we have a cosine function, or not just a cosine function, just a trig function in general. Which one of these trig functions is the most complicated one? And you could do this one with pattern recognition too, right? We know the derivative of cosine is minus the sine. So we can be careful here though. Always choose the one that has the power if we're going to do something like this, and make sure that they're multiplying. So we're going to let u be cosine. Don't make it cosine squared. U just has to be cosine. Okay? And then we have to find du. The derivative of cosine is minus the sine of dx. So notice that it had to end up positive, so we have to put a negative sign in front of the integral there so that it ends up being positive when we take that integral. Alright, so now we rewrite it in terms of u, so it's really just negative the integral of u squared du. Alright, we're easily able to do that integral. It becomes u cubed over 3. Don't forget there's a negative in front. We replace u with cosine, alright, and we're left with negative cosine cubed of x divided by 3 plus c. Okay, so there's an advantage of using u substitution with trig functions, alright? And remember, let it be the more complicated trig function. Cosine squared is more complicated than just a sine, right? The squared makes it the more complicated function. Alright. So now we've done all that with indefinite integrals. Now we need to do it with definite integrals. So when we do u substitution with definite integrals, it's imperative that we make sure we find our new values of integration. All right, we're given our integral with our original a and b, but that's in terms of x. So once you choose what u is going to be, you have to find your two new values of integration, because you're going to integrate based on what u is, not on what x is. So those two limits, a and b of integration, are going to have to become g of a, g of b. So whatever we choose for u, we have to put in those limits, and we're going to have new limits of integration. Okay, so since we're doing change of variables, you have to change your limits based on that. So we're going to do that with u substitution. So you can write down theorem 4.15, but if we work through an example, okay, it's going to make sense. Notice this integral is entirely in terms of x. Okay? We're going to make everything in terms of u. That 0 and that 1, the limits of integration here, are in terms of x. We're going to have to change them in terms of what our u is going to be. U is obviously, you should be able to choose that now as x squared plus 1. Okay? So we should know that that's going to be our u. So we have to know what to use. But we have to find our new limits of integration as well. Okay, so we're going to do this. We know that u is x squared plus 1. That makes du having to be 2x dx, right? Remember, now we have to solve that for x dx, right? Not just dx, because we want to replace, look at the original integral. The original integral has x dx. We have to replace x dx with some form of du. So we have to know that du divided by 2 is our x dx in order to replace du. So very important on that piece when we do our replacement. Now, we have to change our upper limit and our lower limit in terms of u. So, when x is 0, right, that's the lower limit on our integral. I'm going to plug 0 in for x into our u function. So I'm going to have 0 squared plus 1. So my new lower limit for my u integration is going to be 1. In terms of x, it was 0. In terms of u, it's 1. Now I do my upper limit. My upper limit in terms of x is a 1. So I have to substitute it in for the x that we're using in our u substitution. So it's going to be 1 squared plus 1. So our new u upper limit of integration is 2. So now in terms of u, we're going to be going from 1 to 2. When we were in terms of x, we're going to be going from 0 to 1. But now since we've changed our limits, or our variables, right, our limits have to change based on u. So our new limits of integration, okay, are going to change based on our u value. All right, so our original function is above, that's in terms of x. Now we've done a complete u substitution. And this is applied to definite integrals, right, because they have limits of integration. So now when we do the antiderivative and go through, we're going to do everything in terms of u and the new limits of integration that are in terms of u. You have to do this for every definite integral that you do. If you don't, you're going to be wrong. Okay? So now we're going to do just like we've been doing, just like we did in the last section, only now we're going to be doing it in terms of u. And we'll get our finite answer. All right? So we're going to evaluate the integral. I don't need to go step by step here. But when we do this, we get 15/8. Okay? So that should make sense. All right? Once we do complete u substitution, change the limits of integration so that they're in terms of u, then do the antiderivative and evaluate the antiderivative, right? This is literally just doing the fundamental theorem of calculus after we've done our u substitution. Okay, so nothing real new on this piece. It's just understanding that with u substitution with a definite integral, we have to change the limits of integration as we work through this problem. All right, so hopefully that makes sense. Else, watch the lectures in class and things like that as I go through, because I'm going to do more examples, so we can really hone us in and focus on that. All right, and some of you guys, maybe you don't want to watch the live streams or things like that. That's fine. There's plenty of stuff on Khan Academy or things like that as well. But make sure you're getting a good practice. You're going to see, a lot of these on your final. We're going to have a big test on this. And some of you guys, where we are at the end of the school year here, or where we are, at this part of the semester. I mean, not school year, but just this part of the semester. You may be in and out of town or things like that. So, all right. We could have done it all in terms of x, all right, and you still could have gotten the same answer, just a lot more work. So u substitution kind of helped us out, okay? So you can do it in terms of u, like I just showed on the previous slide or on this one, right? Or we could put our x stuff back in for u and use the x limits of integration as well. Either way works. You just have to make sure you're choosing the right limits. If you keep it in terms of u, which is what I would do, and use your u limits of integration, it works out great. Or, once you've done your u substitution and integrated, put your x stuff back in and evaluate using the x limits of integration. Either or, it makes it work. All right, lastly, all right, Understanding if we integrate even or odd functions. Sometimes, they can be difficult to do. So sometimes you can simplify it down so that it's easier to understand. All right. Notice if we have an even function. Remember, even functions are always symmetrical about the y-axis. And remember, you're going to have to test for even and odd symmetry. So remember how to do that. If you substitute a negative x into a function, okay, and you get that same function back, it's even. If you substitute in a negative x into the function and you get the opposite function back, then it's odd. So you have to make sure that you have even or odd symmetry to apply what we're going to do. All right, and it'll make sense, if we have that even function. So things don't, cancel per se as we want. So first thing I would always check, see if the function is even or odd, and go from there. Why? Because we can apply the theorem 416. Okay? If we have an even function, and look at our limits of integration, it's negative a to a. That means we have to have, negative 1 to 1, or negative 2 to 2, or negative 3 to 3. It is important that the closed interval, okay, has to be from the same limits of integration piece. Okay, or the same integer, just with opposite signs of f of x dx. So how can we do that? We can rewrite an even function as 2 times the integral from 0 to a of f of x dx. So that's how we'll do it if we have an even function. If we have an odd function, they cancel each other out and we get 0. So we don't have to do all the integration. We just have to check and see if the function's even or odd, and then apply this theorem to our integrands. Okay, so let's take a look at this function here. We have this function. Notice it's from negative pi over 2 to pi over 2. So we can check here if it's even or odd or things like that. So we have sine cubed of x cosine of x plus sine of x cosine of x dx. So what we can do is check to see if we have even or odd symmetry. So in this case, we're going to substitute in a negative x. And if we get the same function back, it's even. If we get the opposite function back, it's odd. Okay, so when we substitute everything in, if I substitute a negative x into that function, I end up getting negative sine cubed x minus sine of x cosine of x. It gives me the opposite function back. It gives me minus f of x back, right? I know this function is now odd. Okay, so that's important. Since I know this function's odd, I can literally just apply theorem 4.16 and know that that integral, without doing any other work to this integral, right? Because you're going to have to break that into 2 separate integrals, see what works out. Doing sine x cosine x may not be an easy one, or the sine cubed. All right, so those might, it might be a lot more work, but since we just checked for even or odd symmetry and this is odd, I know this integral is 0. The answer is 0 here. And how is it 0? We'll take a look at the graph. Okay, it's an odd function. So the area from the curve on the left-hand side is going to cancel the area of the curve on the right-hand side. So that's very common with odd functions. So that's why we can conclude that, notice the area on the left is negative, the area on the right is positive, and it's the same amount of area. So my negative cancels out my positive, therefore it's 0. So that's really, really helpful when you get a more complicated function. Test to see if it's even or odd first. Okay, that'll help you really make sure that you can either make the integral easier if it's even, right? Or if it's odd, we know it's going to be 0 because the areas will cancel each other out because they're equal areas just with opposite signs. All right, guys. Well, that's the end of this section, end of this lecture. If you have any questions, feel free to email me or let me know if we need a Zoom meet or team meet or anything else like this. Else, see you guys in class. Have a great day.